part D, we're told that the graph of the curve has a horizontal asymptote at y equals c. And so that means as time goes out to infinity, the y value is going to converge to a real number, c. It doesn't have to be 0, but it could be 0. It's just some real number c. And we would write that as the limit as t approaches infinity of y of t is equal to that value, whatever that value of c is. And so what we want to do here is to write but not evaluate an expression involving an improper integral that represents this value c. If you recall what an improper integral is, it is an integral that has infinity as one, or it could be, there are different types of improper integrals, but one is an integral that has a limit of integration as infinity, or where infinity is the limit of integration. And so that's really what we want here. We want to find, again using the fundamental theorem of calculus, we have that at time t equals 2, we do know that the y coordinate is equal to -3, as you can see above. So we're given, we have y of 2, and we're looking for what the value of y converges to at infinity. And so we would find that using y prime of t as the integrand. So we have the integral from 2 to infinity of y prime of t dt. And if we could write it in this way, we would say that that's y of infinity. But what y of infinity really is the limit as t approaches infinity of y of t minus y of 2, and we know that y of 2 is -3. So that's minus -3, which is plus 3. Then by subtracting 3 from both sides, on the left side we would get integral from 2 to infinity of y prime of t dt minus 3 is equal to this y of infinity, but we're going to give that its proper name, and that is the limit as t approaches infinity of y of t, which is the horizontal asymptote. And so that is equal to c. Okay, now we could write the integral from 2 to infinity as the limit as b goes to infinity of 2 to b, for example. That would be fine. But this is sufficient, and this wraps up this problem as well.